Hi everyone, welcome back. I'm Devasatham and you're watching EE635 Applied Linear Algebra lecture number 4, and this is going to be the third and final module of this lecture. So in the first two modules, we have seen two levels of abstraction of the ideas that we are looking at. Yeah, in the first level of abstraction, we have seen that how we can allow the numbers to be not just from real numbers, instead of real numbers, but instead from any arbitrary field. And then in the second level of abstraction, we have seen that we are not constrained by just columns of numbers, but instead we can look at this abstract object called a vector space, yeah, where we have abstractly defined these ideas of vectors through these two very important operations, namely vector addition and scalar multiplication, right? If you remember, we had written out all these axioms which define a vector space. Now in this module, we are going to see, starting from this module onwards, we're going to see what more we can do with this abstract idea of a vector space, right? So this will also be instructive to all of us in the sense that from now onwards, we'll see how we can equip ourselves with this idea of abstract vector spaces and how we can play around these ideas without actually considering, vectors as columns of numbers, right? Doing things from an abstract algebraic point of view. So the first notion that immediately will show up in this case, the first important notion is that of a subspace. And we're going to define what that subspace is, okay? Right, so let me share my screen. Yeah, hopefully it should be up any moment. Right, okay. So as I said, the first notion that we're going to talk about is that of a subspace. So as the name suggests, I'm sure you are able to make out what to expect for a subspace. So what is a subspace? Okay, sub means that gives the idea that it must be a subset. So let's say V is a vector space over a field F, then a subset, of course, has to be non-empty. W of V is called a subspace of V if W is itself a vector space over the same field F with vector addition and scalar multiplication as defined for the parent space V, right? So that means W is a subspace if first of all it's a subset to start with, and then it itself is a vector space. I mean, it is a vector space on its own right, but it cannot be vector space under arbitrary scalar multiplication and vector addition that you may wish to define for W. No, that is not allowed. The vector addition and scalar multiplication that are there for the vector space V must are the vector addition and scalar multiplication operations defined for W also. So under the same two operations, W must also be a vector space. Then and only then we call W to be a subspace. Yeah, let's say some examples must be in order. So we look at our favorite contender for a vector space, namely R2. Yeah, we all feel very comfortable with R2, I'm sure. R2 is x1 axis, is x2 axis. What sort of subsets will be subspaces? Well, um, suppose I take this collection of vectors. So each vector is a point, you know, it's an arrow. It's an arrow, so it can be identified with a point also. Is that a subspace? It's a subspace, all right, but it is not a subspace. Yeah, so therefore, I'm going to use, let's say, different color. So I'm going to use red color for to denote a set that is not a subspace. This is not a subspace. Why? A subspace has to be a vector space, all right? And a vector space must have additive identity, which is 0. 0 is here. This is the origin. This is not there here, not there in this set. So it's not a subspace. So it's not a subspace. Once again, so suppose I draw this line. Is this a subspace? Once again, this also doesn't contain 0. So this cannot be a subspace. Suppose I have this set of points. Is this a subspace? Well, it does contain 0 to its merit, but this also is not a subspace. Why? You see, I can do the following. So suppose I choose this point on this set. This is the arrow corresponding to this point. In order for this to be a subspace, its scalar multiplication, every scalar multiplication must also be there in the set, but multiply this by some number. That will take it, sorry, that will take it, say here. This is not there in this set, so this is also not a subspace. So all these are not subspaces. None of them are subspaces. Okay, so then what will be a subspace in this situation? Well, okay, once again, I'm drawing this R2. Let me write it down also as R2. Look at this. Look at this straight line that passes through the origin. This is going to be a subspace. Why? So let us check, huh? Let us go back to the definition of subspace, of vector space, which is where these properties, the axioms, yeah, right. Now, out of these axioms, first one is automatically checked, you see, because field is already there, no? Because we already have a vector space. There, I'm looking for a subset. So one is there. Number two, okay, that's also there because I already have this W set given to me. So I have the elements for which I have to check that that collection of elements is a vector space or not. Vector addition is something that I have to check. Why? Because W is there, but I have to check whether W is such that, you know, for every element in W, say xi and eta, xi plus eta must also be there in W. That I have to check. So this the first thing I have to check for 3. The commutativity and associativity I don't have to check because they're already there. Okay. So they're already there because it's there in V. So of course the same operation applies in W also. So it's already there in W, right? So I don't have to check it anymore. But I have to check for this 0, the additive identity. I also have to check for the additive inverse. Now, scalar multiplication, once again, all these properties are properties of the vector space, or the parent vector space already defined. So they will already be there. I don't have to check them. Right? These are all, you know, distributivity property and associativity property, and this 1 multiplied by 1 gives me the same vector. These properties are already there for the parent, and the elements in W are already elements in V, so they automatically will satisfy all of them. So therefore, I just have to check whether it's closed under scalar multiplication or not. So this, and this already are checked. So therefore, for a subspace, all I have to check are the following. I will do those checks and write them one by one. So first of all, to check, number one is okay, closed under vector addition. This I have to check. Closed under scalar multiplication. 0 in W, and 4 for all, what should I write? Say small w in W, whether minus W belongs to W or not is what I have to check. These 4 properties I have to check. So first, close under addition, vector addition or not, let us see. For this, suppose I take an arbitrary point here. The arrow that corresponds to this is this one. And then suppose I take another arbitrary point here. The arrow corresponding to this must be this one. So law of vector addition would tell me that the sum of this will be another arrow like this, completing the parallelogram. That obviously is on the same line. Yeah, so therefore this is closed under addition. Check. Close under scalar multiplication. Once again, take any arbitrary vector here. Multiply this. You're going to get something here. Once again on the line. Second point, check. 0 is there. Third point, check. W minus W, of course, pick any W. Then the minus of that will be somewhere here. So number 4 is also checked. So this is a subspace. Now with once again little flight of imagination. So this is example number 1. With a little flight of imagination, in f to the n, any hyperplane passing through the origin is a subspace. Yeah. In R3, any line passing through the origin, any plane passing through the origin, all of them are subspaces. There are trivial subspaces, 2 trivial subspaces, namely just the 0 vector, that set as a subset of V is a subspace always. You can check that it satisfies all the properties, although trivially, but this is subspace. And of course, V is a subspace, is a subspace of itself. These two are 2, as they say, trivial subspaces. Are there more subspaces? Yeah. So you yourself are going to check that if I have square matrices, then symmetric square matrices forms a subspace of F n cross n. So F n cross n is a vector space. In that, if there is, if I consider the subset of all symmetric matrices, then that's going to form a subspace. Yeah, is it all right? So this goes to you as an immediate attention problem. Okay. Yeah. So each time when we face with the challenge of checking whether some subset is indeed a subspace or not, we have to check these 4 properties. But checking these 4 properties may be a little cumbersome and may be a little difficult at times. So for that, we have this very interesting, nice result, which is the first theorem of this lecture. That is the following. What does it say? It says that, okay, so let V be a vector space over a field F, and W be a subset be non-empty, right? Then W is a subspace if and only if for all V comma, right, V is fine. For all V and W in W, and for all alpha in F, alpha V plus W is also there in W. This is the theorem. So look at the statement of the theorem once again and familiarize with yourself with what we are saying here. So once again, the setting is like we have a vector space V over a field F. W is a given subset, which is non-empty. And then I'm claiming that W is a subspace if and only if for every V and W in W, not just closed under addition, but every combination like this, alpha V plus W, where alpha is any arbitrary element from the field, any arbitrary scalar, yeah, and V and W are arbitrary vectors from W, then alpha V plus W must be an element in W. If that property is satisfied, then and only then is W a subspace. Okay. Now, once again, notice that this is an if and only if statement. So I have to prove both direction, right? So let me first prove the only if part, because that is the easier part. Only if. What does that mean? So for this, we assume that W is a subspace. We have to show that for all V comma W in W and alpha in over all alpha in F, alpha V plus W is also there in W. But this I say is trivially true because W is a subspace, right? So if W is a subspace, then it's closed under addition, it's closed under scalar multiplication. So since W is a subspace, alpha V is in W, and hence alpha V plus W is in W. Because W is a subspace means it's a vector space, so it's closed under scalar multiplication, closed under addition, so it has to be true. So this is the only if part. The if part is more interesting. For the if part, we have to assume that for all VW is VW in W, and for all alpha in F, we have alpha V plus W in W. We have to show that W is a subspace, right? That's what we have to show for the if part. Now, I have to show that W is a subspace. How do I show that? I've already listed out the 4 properties that needs to be checked for a set, a purported set to be a subspace, right? It has to be closed under addition, closed under scalar multiplication, the additive identity should be there, and additive inverses should be there, right? Okay, let us see whether that is true or not. We'll go by like this. First, we'll check the following. So since W is non-empty, there exists a W in W, because non-empty means at least one element will be there. Okay. So if one element is there, then -1 times W plus W is an expression of this form. And we've already assumed that such expressions for all VW, that is in the capital W, must also be in capital W. So that means this must there be in capital W. But what we have checked, what you have checked, you are supposed to check from module 2's immediate attention problem. -1 times W is nothing but additive inverse of W. So this is minus W plus W, which is 0. And that means 0 is there in W, right? So additive identity is there. So which means this property is checked. Okay. Now, if 0 is there, so this is property number 3, checked. 0 is there. Now, let V be arbitrary and alpha in F also be arbitrary. So I'm taking an arbitrary vector in W and arbitrary scalar in F. Okay, then alpha V plus 0 is an expression of the type alpha V plus W. Yeah, because this is there in W and we have already checked that this is also in W. So therefore, from our assumption, this must be there in W, which then tells me that alpha V must also be there in W. Pretty easy, no? Yeah, but this means I have checked that this is closed under scalar multiplication. I have taken an arbitrary V and multiplied this by arbitrary alpha, that is there in W, right? So property number 2, property number 3, both are satisfied. Okay, now next, additive inverse. Okay, so let V, once again, let, what should I use? Say U. Let, no, I can use V itself again. Let V once again in W be arbitrary, but -1 into V, okay, this is of this type, no, and we have already shown that this is closed under scalar multiplication. This is minus V and this must belong to W. Yeah, because every scalar multiplication there is in W. So in particular, minus V must also be, -1 times V must also be there, which means minus V is there in W. This proves that this property is satisfied. And then finally, on to the closed under vector addition property. Finally, let V, let U, comma V in W be arbitrary. Then U plus V is, of course, no, this is nothing but 1 times U plus V. So this also is something of this form. Once again, this form, and we have already checked that, we have assumed that such forms are already there in W, which means W is closed under vector addition also. So that means this property is satisfied. So all these four properties are satisfied. So this would imply W must be a subspace. This completes the proof, right? You may ask, how does this help? Well, with this theorem in place, we can now have more examples of such subspaces. More examples. Okay, very interesting. This is something that I've already asked you to check as a homework problem, but this will help you solving that homework problem from module 2. Define S to be the collection of all x's in f to the n such that ax is equal to 0. Yeah, solution set of a homogeneous system of equations, where of course A is a matrix in f m cross n. Yeah, it's an m cross n matrix with entries coming from a field. This is a subspace. Why? You see, say x1 is in S, x2 also is in S, to arbitrary, and suppose alpha is any scalar from the field. Then what happens to alpha x1 plus x2? When A acts on it, this is a matrix, no? I know matrix multiplication rule. From matrix multiplication rule, this follows that this is alpha A x1 plus A x2. But x1 is in the set S, so ax1 must be 0. This is alpha times 0 vector. X2 is also there in S, so ax2 must also be 0. This is 0, so therefore this must also be in S. Now 0, of course, this is 0. So this implies alpha x1 plus x2 is also in S. So from our theorem, it follows that S must be a subspace. This subspace is going to be of immense importance for us. Immense importance. I can't overstate. Right? So much so that we give a name to this subspace. This subspace S is called the null space or kernel of the matrix A, also called null space of A. But we say kernel and we use the symbol ker of A. All right. This is so kernel of a matrix A is a subspace. Similarly, if once again we have, say, a matrix A which is f m cross n, and suppose I define this set, say I, which is by definition collection of all y in f to the m such that there exists x in fn with the property that y is equal to ax, right? Then I is a subspace. Once again, let's do a quick check. So suppose what do I do? So suppose y1 is in I, y2 also is in I, and alpha in f is arbitrary. Now, because since y1 is in I, this implies there exists an x1 in f to the n such that y1 is equal to a times x1, that's as per definition. Similarly, y2 is in I. This implies there exists x2 in f to the n such that y2 is equal to ax2. Okay, so now I look at alpha y1 plus y2. That must be equal to alpha ax1 plus ax2. Once again, this is nothing but a into alpha x1 plus x2 by matrix multiplication rule, right? But see, what form is this? This is a times a vector, but a times a vector are, the collection of all such vectors is the set I. So of course, this also, this, okay, yeah. So this belongs to I. So therefore, you see, y1 in I, y2 in I arbitrary, and alpha in F arbitrary implies alpha y1 plus y2 is also in I. So by our theorem, this means I must be a subspace of F to the n. This also is going to be of immense importance for us, this subspace, so much so that we have a name for it. This subspace is called the range space, or we're going to call it, in this course, we're going to call it the image of the matrix A. So two subspaces, two very important subspaces, kernel of A, image of A. All right. Now, yeah, so we have this this kernel and image of a given matrix. Now we are going to look at something, some more kinds of properties of these subspaces, namely the following. So okay, before we do that, let me give you some immediate attention problems, so that you can solve them and you can be up to speed with what we have been doing. So show this one, show that the set of all symmetric n by n matrices with entries from a field F is a subspace, okay, of square matrices. All right. Yeah. Okay. Now, coming back to lecture. Okay. So now, what we are going to look at is, as I said, some more properties of subspaces. Before that, we are going to look at this one more very special kind of a subspace, which happens to be the following. So this comes under the idea of, the bigger idea of span of vectors. Okay. So let capital S be a non-empty subset, just a subset, non-empty. Okay, actually non-empty is not required. But let's say, okay, let's assume non-empty for the time being. Non-empty subset, just a subset, doesn't have to be a subspace. I define the following set, notice carefully. I define the set of alpha S1 plus alpha 1 S1 plus alpha 2 S2 plus dot 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 up to alpha n Sn, where alpha 1 dot 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 up to alpha n are coming from the field, and S1 up to Sn are coming from the set S. So what I have done is I'm looking at all possible linear combinations of elements from the set S. The set S need not be a subspace. It's some arbitrary non-empty subset, yeah, of V. From there, I'm taking all possible linear combinations, all possible, right? The claim is that this also is a subspace. This is a subspace. Why? In fact, the check is kind of very simple. So suppose, say I have, what should I write? Say I have X, which is equal to summation AI Si I going from 1 to n, one linear combination. So this is a typical, so for the time being, let me call this set as, what should I write? Let me call this W, okay? So then this of course is an element in W. I pick another Y, which is summation I going from 1 to M BI TI. Okay. Let me be absolutely clear. I shouldn't have removed this. Where these SIs are from the set S. And this is also in W. Why? Because we are assuming that this TIs are also in S. You're getting, no? You're getting my point, right? So all I'm saying is nothing profound. It's just, I'm looking at one linear combination of vectors from S, another linear combination of vectors from S. So two arbitrary vectors X and Y from W, where W happens to be, whether W is a subspace or not, I don't know. W is the collection of all possible linear combinations of elements from S, capital S. Yeah. Now, let alpha in F be arbitrary. Then look at what happens to alpha x plus y. Well, alpha x plus y is nothing but summation alpha ai si I going from 1 to n plus summation I going from 1 to m bi di. But this also is a linear combination of vectors from S, no? Yeah, I've just written two sums, but essentially I just have written, this is nothing but a linear combination. Yeah, so then this of course is also an element from W, which means once again by our theorem, see how strong the theorem was, so powerful. From that theorem, we are once again saying that alpha x plus y is there in W for all arbitrary x, y, and alpha. That means W must be a subspace. So this implies W, the way it is defined, must be a subspace. Okay. This W, the way it has been defined, this is called the span of S, denoted by S. If S is a finite set, if S is just equal to S1, S2, dot, 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 up to Sn, only this finite collection of vectors, then often for S, we also write S1 to Sn. And we also, some books also write span S1 up to Sn, or SP S1 up to Sn. Many conventions are there. We're going to stick mostly to this one, or sometimes this one, right? So this is the span. So there is another definition of a subspace. This is also going to be of immense importance. I mean, I cannot overstate the importance of this span idea. This is going to show up in almost every lecture and most likely multiple times. So remember this idea of span. Okay. With subspaces, we also define the following. So if we have two subspaces, W1 and W2 subspaces, both of them, then W1 intersection W2 is also a subspace. You can easily check that. However, and you can make it more. I mean, in fact, no, you can take infinite intersections also. So you can have something like intersection over some index set of Wi. This is also a subspace. Okay. However, one must remember that union of, say, two subspaces is not a subspace. It's not in general a subspace. W1 union W2 need not be a subspace. And the reason is very simple. In fact, you can give immediately many examples. So once again, we come back to our favorite vector space R2. So there, this is x1 axis, this is x2 axis. This is a line passing through the origin. So this is a subspace. This is also a subspace. What is the union? Union is the collection of all this and this. Is this a subspace? No, of course not. For example, I pick an element from here, an element from here. Both of them are there in the union. Their sum is this one. Is it also there in the union? Of course not. It's outside the union. The union contains only this line and this line. So this is not a subspace, right? However, this is a subspace. You see, one can define W1 plus W2, right? This is defined as the collection of all W1 plus W2, where W1 belongs to W1 and W2 belongs to W2. Yeah, this is a subspace. So this goes to you as a homework. Show this, that this is indeed a subspace, right? This is homework. Another homework is show that W1 plus W2 is nothing but the span of W1 union W2. It's not an easy problem, an easy kind of trivial, but it will require some amount of work, some amount of thinking. So do that thinking. It's good to do some thinking at times, right? Yeah, so this is about sum and intersection. So some more um, immediate attention problems, which will make you, which will help you in familiarizing yourselves with the idea of intersection and addition of subspaces, namely this one, and span. So here I'm asking you to, so I'm giving some vectors in R4 and I'm asking you to write down explicitly the span of these vectors. In fact, prove that the span has this form, this parametric form. And another immediate attention problem is that over for F2 cross 2, that's our vector space, the parent vector space, I have two subspaces defined like this and this. I'm asking you to show that the sum is all of F2 cross 2 and the intersection is span of this vector. Okay. Span of a single vector is very easy to understand. I'm sure you understand what it really means. Okay. Before we finish, I would like to point out this particular fact about these subspaces and span. Um, you see, there is one terminology that is quite often used in abstract linear algebraic studies, namely a smallest among all possibilities. So what do we mean by that? Let me clarify. So suppose, so let S be a non-empty subset, just a non-empty subset. Yeah, we have seen what we mean by span of S. So span of S is often said to be the S is the, so notice carefully what I'm writing, is the smallest subspace containing S. Let me elaborate. What do I mean by the smallest subspace containing S? What is the idea of small, big here? What do I mean by that? It means the following. So smallest subspace containing S means uh, if W is a subspace and S is a subset of W, that is W contains S, then S must also be there in W. In that sense is the smallest. That means, so this is my set S. The span of S is a subspace that contains S certainly. Now, if there is any other subspace that contains the set S, it must also necessarily contain span of S. That's why span of S has to be the smallest one. Yeah, there is no escaping it. If there is a subspace that contains S, it must also necessarily, it had better contain span of S as a subspace. Yeah. Now, how do we prove this? Well, in fact, the proof is quite simple. So first of all, we need to notice the following, then how does one define this smallest kind of thing? Well, okay, let us do the proof, and we'll see as we go along, we'll see what happens. Yeah. So once again, you see, we are um, so okay, so let us first notice the following. Okay, so let us define um, so let us define the following family. Yeah, family, that is, it's a collection of all W such that S is contained in W, right? Now I define this object. Let me call it W star. W star is defined as the intersection of all W. Okay, one more thing I forgot to write, which is actually essential. I should not skip that. SSW and oops, and W is a subspace, yeah, subspace of V, right? And W is in F. So I look at the family and I look at the intersection of all those W's in the family. that I define as W star. So notice that W star happens to be the smallest, uh, happens to be the element that is contained in all the W's, right? That is how W star is defined. That is how intersection is defined. So intersection of, hang on a second here. I have to put my laptop to charge. My battery is draining. Right. So as I was saying, this W star must be the element that, so W star contains all those elements which are there in each of these W's. Right. So therefore, W star is contained in every W. So W star, let me write it properly. W star is contained in every W that belongs to that family. What we will show is, so it is enough to show that it is enough to show that S, the span of S is equal to this W star. Yeah, because that is what we want to show, right? W star is such that W star is contained in each of these W's, and our claim was that S must be so. So therefore, it's enough to show that S is equal to W star. Okay. So for that, once again, it's equality of two sets. So we have to show it like this, both directions. So suppose we'd like to show this one first, that S is contained in W star. Okay, so how do I show this? Of course, W star is a subspace, right? Because it's intersection of subspaces, and we have seen that intersection of subspaces is a subspace. Right. So yeah, right. First, we notice that S is contained in W for all W in F. So this, of course, implies S must be contained in W star, but W star is a subspace. So this implies any linear combination of elements like this. So this is a typical element in the span of S. This must be there in span of S, but this must also be there. This must also be there in W star, because W star is a subspace, right? Oh, let me rewrite it properly. Yeah, I think it may not be clear. My writing was not proper here. Let me do it. Let me do it properly. So W star is a subspace. So now consider a typical element in S, that is summation alpha I Si, I going from 1 to n, where alpha I is in F and Si is in S. Then all Si's are in W star, but W star is a subspace. So this implies summation alpha I Si, I going from 1 to n, must also be there in W star. Right? So this proves that this direction is there. Okay. Now, on the other hand, when we have to show the other direction, the W star is contained in span of S. What do we do? Um, so let us see. W star is the intersection, right? Yeah. So S is a subspace. By definition, when I'm looking at all possible linear combinations, I I can look individual vectors also. So that way, S is contained in span of S. But then this implies this span of S must then be a part of the family. But W star is contained in every element in the part of family. So therefore, this implies W star is contained in S. And that is what we needed to prove. This completes that, right? So this is how we show that, that the span is the smallest possible subspace contained containing a given set. Yes. All right. So let's call it an end for this lecture, lecture number 4. We will come back with lecture number 5 with much more details about the abstract idea of vector spaces. Namely, we'll talk about dimension, we'll talk about basis, we'll also talk about an idea called coordinates. Okay, so till then, you okay, watch these videos, and of course, as I've kept on saying, ask questions. You have several fora for asking questions. You can ask questions on the Google Classroom stream. You can ask questions by putting your posts on the YouTube videos. Okay, you can also write to me directly. You can send me uh, email. Okay. What else? As I have said once again before, that it's utmost important for you to see these video lectures, to watch these video lectures, solve the problems there, and then attend the live interactive sessions also and ask questions. For the live sessions also, you can ask questions. Um, these things that I have discussed here, all of them almost exactly can be found out from Hoffman and Kunze's linear algebra book, which happens to be the textbook for this course. So I urge you to go and please read that book. Anything that is not clear, you should consult the book. Do not rely only on the video lectures and the class notes. The book is also very, very important, right? And that is why I'm sticking to only one single book, so that you don't have to go through various different material. One single book, I'm following almost, you know I'm following the sequence also. So therefore, it's not just advisable, it's a request. It's an earnest request that you go and read the books. Okay. So right, so I guess that's it. um, so So this is an end for lecture number 4. We'll meet again for lecture number 5. Till then, you please take care of yourselves. You stay safe, stay healthy. And okay, once again, there is no harm in repeating myself. Please ask questions. Okay. All right then. Thank you. Bye bye. Take care.